Okay, guys, you know the drill. Start scanning the QR code. Is it working? Is it working? Is it working? Can you guys hear me?
Yeah.
Okay, we're all good. Okay, so are you guys ready for chapter 14? Finally? Are we ready? Really? Not that ready? We don't want to get ready for that? Okay. So, as you probably saw in the handout, we only have 3 pages. So it's a very short chapter. Okay? Very simple. We basically have 3 different systems. We have to learn how to classify them. And then we're going to go back to talking about molecular orbital theory, but this time for cyclic structure, which is slightly different. Okay. Let's start simple. So let's start with the concept. Okay. So in this case, it's all going to be about the stability of the molecule. Okay. So far, the only aromatic molecule that you guys know for sure is your benzene group, right? Now, what's the difference between a benzene group, something that's cyclic, versus a linear conjugated molecule? Which one is going to be more stable? Why the benzene? So, yes, in a way you're correct. So especially because it's a cyclic structure, the resonance is going to be moving throughout the entire molecule equally. For something that's linear, that might not be the case. So in this case, we know that an aromatic system is going to be better than a conjugated system. Okay. In this case, let's just write aromatic. Now, we're still talking about benzene. Now, technically, we can call it 2 ways. Just your benzene, or we can say cyclohexatriene. That's the full IUPAC name, let's say. Now, technically, even though they're both going to be drawn the same way, your benzene group is going to have higher stability than the cyclohexatriene. Okay, it's going to have higher stability. And now let's look at the Y on the next page. Okay. So it's practically all about the orbitals. Okay. So your benzene group, we have sp2 carbons. So we know that those orbitals are going to be overlapping each other. That's why we see that pattern on the right molecule. It's just a continuous pattern of red and blue. Okay. Now for the cyclohexatriene, technically we're looking at each p orbital individually. Okay. They're not overlapping. That's why benzene is going to be more stable than cyclohexatriene. And if you want to learn more about this, I put a little conceptual thing in there so you guys can read it. Make sure to answer some of the questions. And then we have a little energy diagram. Okay. So your benzene group, pretty symmetric. Everything's cool. Everything's nice. It has lower energy because it's more stable. But the cyclohexatriene, it can be drawn a little bit differently, like that. Okay. So the angles are not ideal, which is going to make it less stable and with more energy. Okay.
So the resonance of that not bad.
Exactly. So again, this is just the conceptual portion. Do you have any questions so far on this? We're just talking about orbitals, how they overlap, and that's it. Okay. Now, for this class, we have 3 different systems, okay? We have our aromatic molecules, we have our non-aromatic molecules, and we have our anti-aromatic molecules. Okay, now, they're actually in that specific order. The aromatic one is going to be the most stable system. Then it's going to be non-aromatic, and last one, anti. So let's just put a little, whoops. Let me redraw this. Okay, that's the order of stability, okay? We want to have something that's aromatic, then something that's non-aromatic, and last one is going to be something that's anti-aromatic. That's really unstable. Before we go over the requirements, has anyone read the book on this or looked at any of this? Aromaticity? Nothing at all, not even the slides? Nothing at all. We just know what he talked about in lecture last time. And that's it. Okay, so that means that I'm introducing this topic first, so let's see how that goes. But first of all, the ones of you who came in late, please scan the QR code. And since I'm the first one to introduce it, we're gonna go slow today. Okay, did we scan it? Okay, I see some people scanning. Okay, we're good. Okay, let's start with the aromatic portion. So there's gonna be 4 main requirements to consider a molecule to be aromatic. The very first one is really simple. If it's cyclic, that's gonna be one of the requirements. So in here, let's just write something that's cyclic. Okay, so as long as you see a little ring, it follows that criteria. Now, next aspect is that it has to be planar. We know that double bonds overall are gonna be planar. So that's pretty straightforward. Now, next aspect is gonna be that the molecule has to be fully conjugated. So what does that mean? Fully conjugated. How do you know? Yes.
One bond away.
It has to be one bond away from each other, exactly, that little sandwich pattern. And also remember, all of the carbons have to be sp2. If we see a carbocation, radical, carbon ion, those guys are going to be considered sp2. We talked about this in the previous chapter. So in here, let's just write fully conjugated, which means that all of them are sp2 carbons. Okay. So far, we're good. Pretty simple requirements. Okay. Now, the fourth one is going to be the most important one. It's going to be called Huckel's rule. Okay, that's just a theoretical name. That's just the actual name, sorry. Huckel's rule. Now, Huckel's rule gives you a little formula, which is going to be 4m plus 2. Now, for that formula, whatever number you get is going to be the number of pi electrons that you have in the system. Okay, now, here's the thing. N is not equal to the number of pi electrons. N can be any whole numbers. It can be 0, 1, any of those guys, okay?
So what does N predict that? What I don't understand.
N itself, it doesn't predict anything. The formula just gives you the possible number of pi electrons that you have for an aromatic system. Now, again, N, we're just plugging in any number you want. It doesn't mean anything, okay? It can be any number. Now, what's important is the possible numbers that you can form, okay? So in this case, your possible numbers are going to be 2, 6, 10, 14, and 18. Those are the basic ones. Technically, we're going to have a few other options, but usually we're not going to look at something bigger than just 18 pi electrons. And remember, those numbers are going to be equal to the number of pi electrons. Okay, so far we're good? Okay, now let's go back to our benzene group. Now, benzene, let's go through each of the requirements. It's cyclic, it's planar, it's fully conjugated because all of the carbons are sp2. And then for Huckel's rule, we have to see how many pi electrons we have. So for a benzene ring, how many pi electrons do we see? 3? We see 6. Exactly. Now we have 6 pi electrons in that molecule. Now, next thing is to see if that number is one of the possible numbers of Huckel's rule, which we find it actually right here. So that means that the molecule is aromatic for that reason. Okay, that's how going to be how you're going to apply the rule. So for questions, so yes. So whatever you plug in into Huckel's rule, it can be any whole numbers. The N doesn't represent anything in the molecule itself. That's the confusing part of this chapter. N can be any number you want. The important part is the possible results that you get.
Sorry, so you have to have, so the ring has to have one of those numbers.
In order to be considered aromatic.
Consider aromatic.
Exactly.
It has to have an N number.
No. It has to have one of those possible numbers at the bottom here. So let's just actually,
Okay, so
And it's
in
how you get those numbers, so you plug in
so
zero
in the
for n,
example,
you get.
so in the
exactly.
So in the example of the benzene ring,
Mhm.
electrons are 6, so
If we see that 6 is one of the possible numbers in Huckel's rule, then we're good. You can solve this all actually backwards as well. Whoops, that's not the correct one. Okay, 4n plus 2. If we're talking about our benzene group, we know that the number has to be equal to 6. So simple algebra, this guy is going to be 4, which means that n is going to be equal to 1. Now, 1 is a whole number, so that's any number that we can plug in into 4n plus 2. Again, n doesn't mean anything. It's any whole number. Yeah.
and what does that accomplish by plugging in then afterwards?
So you confirm that you have your pi electrons.
So what is the like point of Huckel's? What is it? What is it?
Okay, here's the thing. Huckel's rule just tells you the number of pi electrons for any aromatic systems, which is the highlighted part. Okay, so that's 2, 6, 10, 14, 18. Now, and it doesn't mean anything. That's just one of the variables, let's say. 4 is always there, 2 is always there, and it can be any number from 0 all the way to, I don't know, 100. Okay.
So according to the aromatic ring that we have, we can figure out n.
Yes.
Yeah.
I
So
think
The
what's
whole is not-
relevance of-
what's.
So why bring it up in the first
Okay.
place?
Because you have to know this. Because he might ask a conceptual question or what's the
That's it.
formula
That's-
for
that's
Huckel's
all.
rule.
But if you.
Just focus on the
Like,
highlighted part.
Great.
plug
That's what
in-
you're looking for. Highlighted part.
plug
That's it.
in Zero for n, you get 2, plug in 1, you get 6, plug in 10, you just memorize that sequence.
Yes.
It just-
So you can either do the math on the spot or like most people, you can just memorize the highlighted part. That's it. Okay, questions so far. And you guys can actually ask your professor what's n, because
Press it.
I asked Rose.
it's any number. Yeah, it's nothing. Yeah. And it's nothing. Yeah, it's just a constant. Okay, so far questions on the aromatic portion. So far we're good? We kind of got it? We kind of got it, okay. Okay, now, to be not aromatic, this one is simpler. Why? Because as long as you break any of the 4 rules from being aromatic, you're considered not aromatic. So in here, let's just write
Break any of the.
breaks any of the 4 rules. So let's look at this little molecule. Okay, and let's go through the criteria for aromatic. First of all, that molecule in blue, we know it's cyclic. We know it's planar. Is it fully conjugated? No. So, because we're breaking the fully conjugated rule, it's going to be a non-aromatic molecule. Okay, so far we're good. This one, it's simpler.
Also, it doesn't follow.
Yes. Okay, are we ready for the anti portion? We're good. We're still taking some notes.
Pairs considered pilot.
I'm sorry, what?
Are both pairs considered pilot?
Depends. If we are looking at carbon ion, then yeah, for sure.
They're looking at pilot.
Yes.
So does it follow any of the rules and especially.
It can follow 3 of the rules, but as long as it breaks at least 1, no matter which one it is, it's non-aromatic.
So it can follow a couple of rules?
In this case, it can, because the number that we would get, how many pi electrons do we see in this molecule? 4. Is 4 one of the possible numbers in Huckel's rule? No.
So as long as it breaks one of those rules, it's not gonna.
In this case, this molecule broke 2 rules. But again, the requirement is just at least break 1. That's
But I
not
have
what
a
I want.
question. So if it breaks any of those rules, will people's rules still be satisfied?
Sometimes, yes. So far, questions. I see a lot of people talk. We're just chilling. Okay, we're just chatting. Okay, for the anti-aromatic portion. Now, the first 3 rules are the exact same. So that means that the molecule has to be cyclic, planar, fully conjugated, which means that all of them are sp2, And now, here's the thing. Aromatic and anti-aromatic are gonna be different only because of the fourth requirement, which is the little equation that we saw. In this case, it's not gonna be Huckel's rule. The formula is just gonna be for N. The formula, it doesn't have a name, okay? So don't ask me for it. It doesn't have a name, period. Now, again, N, it can be any number. We don't care about N. What we care about is the possible numbers that we can form, which in this case are gonna be R number 4, 8, 12, and 16. So again, we're only gonna focus on the highlighted part. As long as you get any of the highlighted numbers in there, the molecule is gonna be considered anti-aromatic, okay?
Can it go up to?
Yeah, but usually you're not gonna see anything bigger than 18 or 16, yeah.
So just to confirm, anti-aromatic also not aromatic?
No,
Okay, so should we change our example then for not aromatics?
let me show you an anti-aromatic problem. Let's do this. Okay, random molecules, okay?
So just do that.
Yes. Radicals are considered sp2. So yeah, they're gonna be donating one pi elect. Okay, now, really quickly, let's go through the requirements. The molecule is cyclic, it's planar. Is it fully conjugated? Exactly.
Yeah.
The radicals, remember, radicals are sp2. So everything in that molecule is sp2, which means that it's fully conjugated. So we have the third requirement. Now, very last requirement, how many pi electrons do we see in total?
Or,
Damn, this is not an anti problem. But in this case,
so those radical electrons are pi electrons.
yes. So we have 1, 2, 3, 4, 5, 6.
Yeah,
Six. No, this is another example of aromatic. Now, let's look at another molecule. Let's see.
but the pi bond hasn't formed. It's technically aromatic.
It's going to be aromatic because it follows the rule of fully conjugated. Okay, for the next one, the square one. It's cyclic, it's planar, is it fully conjugated?
Yes.
Yes. Okay, how many pi electrons do we see?
Four.
Is that going to follow Huckel's rule or the anti-rule?
Yes.
Anti-rule, therefore the molecule, it's anti-aromatic.
Wait, why? It's cyclic, it's, I know it's not aromatic.
Just because of the what's it called, the formula. If it
Mhm.
lands on 4 or 8, then.
Oh,
it's
okay, yeah, you're right.
If it lands on
And then
2,
with the
6, 10, or et cetera.
Yeah, it's four. So why would example two not, why would example not be anti-aromatic for the pilot?
It has
Not
4 pi electrons,
conjugated.
but is it fully conjugated? As long as you rate at least one of them, it's gonna be non-aromatic. Yes.
Can you explain what planar means again?
Planar is basically that it's on the plane of the paper. There's nothing sticking out, there's nothing sticking out. Up or down, yeah. Everything is like a sheet of paper. That's it. What do you mean? Oh, yeah. Actually, for this chapter, I don't think you're gonna get bicyclic structures like that. They're just gonna be fused.
What's an example of like a non-planar?
Of a non-planar one? Great question. That's gonna be for any rings that are with 8 members or more. So 8 carbons or more. And here's a tricky part again. It can choose to be planar or non-planar. Okay?
Yeah, because hexane is more preferred in the care complex.
Okay, now. We know the basic rules for the for the for the 3 systems, right? Okay, so far, any questions on the system? We're good? We know that N, it means nothing. We're just focusing on the possible numbers. That's it.
Yeah, she keeps repeating it.
Yes, because I know that I'm gonna get at least one email asking for what's N.
X, and it makes sense.
Okay, yes. Change it, change the N for X.
That doesn't help.
Never
So-
Cool. Okay, now. Here's the thing. whenever we have any heteroatoms in our cyclic structures, they are gonna have some special rules. Very first one that you have to know is with single bonded heteroatom. So let me give you a molecule of that example. Okay, we have that oxygen. Okay, this molecule. It's a little epoxide looking thingy, but we have a double bond. Let's go through the requirements. Is it cyclic?
Yes,
Is it planar?
yes,
Is it fully conjugated?
no,
Okay, here's when the rules come into play. In this case, we have a single bonded oxygen, right? Now, the rule for single bonded heteroatoms in general is that they get to choose, okay? They get to choose to be either sp2 or sp3. So for that portion, we're gonna do a little chart to see what the molecule thinks, basically. So we're gonna have the sp3 area and the sp2 area. What happens if that oxygen chooses to be sp3? What kind of system would we get? It's gonna be cyclic, planar. Would it be fully conjugated?
if it gets another pair like.
Let's just look at the sp3 configuration. Let's assume that that oxygen has chosen to be sp3. Okay. Now, the molecule is still cyclic, it's still planar, but if it's sp3, would it be fully conjugated? No. So that means that we have what kind of system?
Nancy.
Non-aromatic. Thank you.
And he's still conjugated.
Right,
Mhm.
And
Okay, now, hypothetically, let's say that the oxygen now chooses to be sp2. We're looking at two different scenarios. Why? Because the heteroatoms that are single bonded, they can choose. Okay. Now, if they are sp2, the molecule is still cyclic, it's still planar, and now it would be fully conjugated, right? Now, it's fully conjugated so far. Next aspect is to look at the pi electrons that we have. Now, for single bonded heteroatoms, they're going to be donating 2 pi electrons. So it's basically going to be like a carbon ion in a way. Okay. So in total, how many pi electrons do we see?
one. Oh, four, wait. Six.
No,
Two
but
lone-
I think
two-
only
two
one
pairs
of
and
the-
lone pairs
one
and
of the
pi
pairs actually acts the pilot.
Okay.
That's what I.
Or does the
So-
oxygen,
so,
does the oxygen lone pairs start to count as pi bond? I mean, as pi electrons?
I think only one of them.
One of the pairs is going to count. It's going to be like a carbon ion.
Only one of the pairs.
So yeah, we have 2 pi electrons from that oxygen, and we have 3 and 4 from that double bond. So that gives us a total of 4 pi electrons. Okay. 4 pi electrons. Is that going to follow Huckel's rule or the anti-rule? Anti-rule. Okay, beautiful. Now,
Um,
yes.
So how do we know what's sp3 or sp2?
It's going to be up to what kind of heteroatom you have.
Oxygen is always sp2.
No, it can choose to be sp2 or sp3. Now, hold on a minute. Okay, I know that you guys are getting confused, but I know this is the confusing part of this chapter. Now, we know what's going to happen in both hypothetical cases, right? If it chooses to be sp3 or sp2. Okay, now, the choice is going to be based on what's going to give it the most stable system. So, what's more stable, non-aromatic or anti-aromatic? Not aromatic. Anti is the worst one. We don't like it at all.
But anti is fully conjugated.
Yeah, but the problem is the pi electrons.
Okay.
Okay, so Na is more stable than your anti-rule.
Oh, right.
And more stable. So that means that the molecule, in this case, is going to choose to be sp3. So overall, the entire system in that molecule is just non-aromatic. Okay? That's going to be how you're going to be using the rules. I know it's confusing, but so far questions on the first one.
So what's the difference between non-aromatic and, was it
Anti-aromatic, yes.
anti-aromatic?
Yes, it's a stability. This is a specific ranking of a stability. Most stable, aromatic. Second most stable, not aromatic. Third one, the ones that we hate, anti. Okay, that's just the ranking, yes. You can think about that, or you can just think that we're only gonna use one pair. So this is just based on the rules. Single bonded heteroatoms, like that oxygen in there, if it chooses to be sp2, that means that it's gonna have some pi electrons. The number of pi electrons that it has is gonna be 2. That's for the second rule, actually. Yes.
Aromatic, is it the Hubble's rule? Because both examples have 4 pi electrons.
That one of them breaks one of the 4 rules.
So.
Non-aromatic, it breaks one of the 4 rules.
So anti-aromatic follows all the rules, but not aromatic break. So it doesn't always have to break them.
Yes.
Okay.
Now, here's the thing to notice. In both aromatic and anti parts, the Y portion is something that applies to both systems, okay? Those are the 3 requirements that apply to both systems. The green and the red, that's telling you the main difference between aromatic and anti-aromatic, okay? That's the thing that you have to watch out for. And then non-aromatic, it breaks any of the 4 rules. So far, questions? Yes.
It's not aromatic, right? Which rule is aromatic?
Because now we're learning the rules for heteroatoms. Heteroatoms are going to tell you something different. We're adding more rules, basically.
Heteroatoms or anything but carbon,
So oxygen, I'm sorry?
because you added a heteroatom.
Heteroatoms, they have special rules. And again, heteroatoms, they can be any atoms that are not carbon or hydrogen. Okay,
So
let's,
would say nitrogen have the same rules with the
Yes.
pi electrons, it's just only the first 2, that's it.
okay, now, let's look at the second rule. What happens whenever you have multiple single bonded heteroatoms? So let's say that we have this molecule. Okay, now, I know it looks a little funky, but I'm just doing this for the sake of explaining this new rule, okay? Now, let's go step by step. Is it cyclic?
Yes.
Is it planar? Is it fully conjugate?
I don't know
Why
what
would it be?
Oh, because there's a negative charge right on the left.
Exactly. Remember, carbocations, carbon ions, and radicals, they're all going to be sp2. So now, here's the thing. We know that those guys are going to be sp2, but we have oxygens again. So we have to be careful. Now, here's the thing. The second rule is basically applying the first rule, but the choice has to be equal for both heteroatoms. Okay, so both oxygens have to choose to be sp3, or both have to choose to be sp2. Okay, now again, let's do that little chart. Let's see what happens if it's sp3. Let's see what happens if they're sp2. If both oxygens, if they choose to be sp3, is it going to be fully conjugated? No. So that means that we're breaking one of the 4 rules, which means that the system is
Anti-aromatic.
No, non-aromatic.
non-aromatic.
Oh,
be
it's-
sp2, they're both gonna want to be
So
sp2.
it's aromatic,
Now.
not anti-aromatic.
If it's sp2, how many pi electrons do we see? We have 1, 2, 3, 4. Remember, each of the single bonded heteroatoms gives you 2. So far 4. And then the carbon ion gives you 2 as well. Carbocation gives you 0. So that means that the total is going to be 6 pi electrons.
How is oxygen sp2 and sp3 at the same time?
We're seeing both scenarios. Technically, it's sp2 whenever it contributes to resonance, and technically it's going to be based on the geometry of the molecule. But again, that's getting more into the theory. Let's try to simplify this as much as we can. Okay. So 6 pi electrons. Is that going to follow Huckel's rule or the nth rule?
It's aromatic. Does something.
It's going to be Huckel, so it's going to be aromatic.
That's 2.
Exactly. So in this case, because we know that aromatic is more stable than non-aromatic, it's going to choose to be sp2 for that reason. So this guy can be aromatic. Okay,
So which is more stable?
in that case, it was sp2,
Why?
because it gives you the most stable system, which is aromatic. First is aromatic, then non-aromatic, last one anti.
Oh.
So far, questions on the first two rules? Time out. Okay, we're processing it. That's okay, we can take it slow. We're just going over the rules, yeah. Those are gonna be your carbocations, carbon ions, and radicals. So plus, negative, dot.
If it's non-aromatic, it's just holding on to its electron. It's not
Mhm.
contributing.
Exactly.
And it's sp3 because it has all 4 electrons around it.
Okay, are we ready to see the third rule for heteroatoms? Sure, we're not that excited. I know it's a lot. Okay, let's look at this little guy. What can I give you? Okay, now, next molecule, the little square looking thing with a nitrogen. Okay. So let's do the same process. Let's go through the requirements. Is it cyclic?
Yes.
Is it planar?
Yes.
Is it fully conjugated?
Yes.
Yes, because in this case, double bonded heteroatoms, they're always going to be sp2. So everything's sp2. We're happy fully conjugated. So last aspect that we're looking at is the number of pi electrons that we have.
Wait,
How many do we see?
4.
6.
Oh, right, no, 5. 1.
Yeah.
And then go to 2.
Okay, let's go right to left in this molecule. So let's start with the easy part.
The 2
Are-
pi bonds. 4.
This is 1, this is 2. Remember, each of those carbons gives you 1 pi electron.
Yeah.
Now, left side, on the carbon, it also gives us 1. Now, the rule for double bonded heteroatoms is that it donates 1 single electron. Okay,
Oh, so 4, okay.
so it's going to be a total of 4. 4 pi electrons. Is that following Huckel's rule or the anti-rule? Anti-rule. Therefore, this molecule is anti-aromatic. Question. So far, we're good. Okay. We're seeing how everything takes into play. Which one? So the nitrogen is always sp2. Why? Because it's a double bonded heteroatom. The only choosing part is with single bonded heteroatoms, and that's it. Okay. Are we ready for the last one? Last. Okay, let's look at a molecule that looks like this. Okay. Let's look at that little triangle at the bottom with boron. Is it cyclic?
Yes.
Is it planar? Is it fully conjugated?
Yes.
Yes, boron, it's always going to be sp2. Now, everything is sp2. How many pi electrons in total do we see?
If 1 doesn't go in,
Just 2. Yeah.
Just 2. Boron doesn't give you anything. So boron is technically going to be like a little carbocation. It doesn't contribute anything.
Okay.
So that's a total of 2 pi electrons. 2, is that following Huckel's or the anti-rule? It's following the Huckel's rule, which means that it's aromatic.
wait, so what does Huckel say against the island?
Oh, here it is. This is double.
Hold up, so we're saying 4n as a number of what?
Don't focus on it.
Oh,
Don't focus on it.
Don't do that to yourself.
No.
You missed the whole episode.
Yeah.
Just focus on
For those of you who just came in, do not look at the equations. Just look at the highlighted numbers.
Essentially, the difference between aromatic and anti-aromatic is that the number of pi electrons in aromatic always land on 2, 6, 10, 14. So it's increments of 4 starting at 2.
Okay.
Versus anti-aromatic, it's just increments of 4.
Okay. Smooth. Yeah.
Okay, we're good?
Okay, I see.
We're on the same page.
We got.
Nobody cares what it is.
We don't care about N. We don't care about N. We just care about the possible
You
number.
know, Huckel's number.
Yes,
Then it's
then it's aromatic.
aromatic.
Just look at the highlighted portion, that's it. Only.
Why?
I have no idea. One of the chemists that invented this rule.
I'm very-
Your professor is actually probably gonna talk about him, so. Okay, now. Technically, the next concept and last concept of the chapter is going back to the molecular orbital theory. Now, I'm gonna leave that page 2 for the very last thing that we're gonna do for this handout, okay? Right now, I just wanna focus on the 3 systems that we just went through and the rules, okay? So let's jump into practice problems right now.
What are those practice?
Whoa, whoa, whoa. Are we still taking notes on this? Are we good to move on?
Yeah.
Okay, we're good. Okay. Let's start over here. Very simple. Okay, now, again, let's apply the 4 rules. Is it cyclic?
Yes, yes.
Okay, it's cyclic, beautiful.
It's
Is it planar? It's planar.
It's conjugated.
Is it fully conjugated? Yes.
How do we know if it's fully conjugated, if it's just a 3 carbon ring?
Fully conjugated means that all of the carbons have to be sp2. Every single member has to be sp2.
Oh, that carbon is not, because it's got the 2 hydrogens.
Oh, okay, so.
It's not fully
So
conjugated.
this is non-aromatic.
Okay.
That's non-aromatic.
Exactly.
Because it still follows people through. We're having 2.
Yeah. But as long as you break one of the 4 rules, non-aromatic. We did this one, I think.
Non-aromatic.
No, it's just aromatic, just because everything's
Yeah.
sp2, it's all conjugated.
It's anti.
So.
It doesn't follow Huckel's rule. It follows the anti-rule.
Yeah.
Because it's.
So yeah, anti-rule.
So the difference between aromatic and Huckel numbers versus.
Yes.
Okay.
Okay,
This next one. What kind of heteroatom do we have? Single bonded or double bonded?
single bonded, so.
What was the rule?
Donate 2 electrons.
Go back to the rules really quickly. Go back to your notes. What was the whole deal with single bonded heteroatoms? It donates 2 electrons and it can choose to be either sp2 or sp3. So we have to do the little chart.
Okay, but if it's double bonded, it only donates 1, right?
Exactly. Now, is it cyclic?
Yes.
Planar?
Yes.
If it's sp3, is it going to be fully conjugated? No, so we know that it's going to be non-aromatic if it chooses to be sp3. Now, if it chooses to be sp2, it's fully conjugated. So last aspect that we're looking at, number of pi electrons. How many do we see?
4 pilots.
5. You said, okay,
Four,
so it's
five.
single bonded, it donates 2, you said, right?
Is it 6?
So, okay, 6.
6.
It's 6.
Okay.
Because remember,
Whatever it happens.
Right,
single,
it's-
whoa,
it's
that's not
Nice,
right.
great.
bonds,
Yes.
and then it has a 2 lone pair. And because it's single bonded, then it would, do the 2 electrons.
Okay, 6 pi electrons. Is that following Huckel's or anti-rule?
Huckel's
Huckel's, so it's aromatic. So is it going to choose to be sp2 or sp3? sp2, there we go.
Oh, wait, how do we know if it should be one versus the other?
Because you have to know what's going to be more stable. What's more stable, aromatic or non-aromatic? There you go. Next molecule. What kind of heteroatoms do we have? Single bonded, double bonded?
Double bonded.
Single
Oh,
bonded, single bonded.
Single bonded, and we have multiple. So what's the rule for those guys?
They each contribute to it.
Hmm,
So then it's gonna be 2, 4, 6, 8, yeah.
So it's not following the anti.
So A, I'm causing,
Anti.
Okay.
100%.
Actually, we need time for this.
Okay, now let's go step by step. We know it's cyclic, we know it's planar. If it chooses to be sp3, remember, both heteroatoms, they have to agree with each other if they're single bonded. If they both choose to be sp3, what's the system?
So sp3 is non-conjugated,
So it means that I have what kind of system?
non-aromatic.
Non-aromatic.
Why? Because you can't count the electrons on the oxygen.
Now, if they choose to be sp2, we know that each of those oxygen is gonna give me 2. So that means I have 2 here, 2 there.
So it's SP3, it's always non-aromatic because it's not fully conjugated.
So it'd be SP3, so we'll say that.
How many? We have 8. Is that following Huckel's rule or anti?
That's anti.
Anti.
What am I gonna choose to be, sp3 or sp2?
That's
sp3.
Exactly.
Non-aromatic.
Non-aromatic is more stable.
Okay, do we see the pattern now?
Yes.
Is it getting easier as we go through the problems? Okay, next one. Now, here's the thing. Once you start getting bigger rings, you have to be careful if they have 8 or more members.
Did you say it's not?
If it's 8 or more, it can choose to be planar or non-planar.
Oh,
Same rule with the heteroatoms. Same thing. It chooses to be planar or non-planar in this case. In this case, how many carbons do we
It's
see?
more stable when it's planar, right? It's aromatic.
Sometimes. You have to be careful. In this case, let's go step by step. Is it cyclic?
Yeah.
Is it planar?
You don't know that. You know that.
How many carbons do we see in that molecule?
8.
8. So again, that little chart, it can choose to be non-planar or planar. If it chooses to be non-planar, I'm breaking one of the rules, which means that I have what kind of system?
Non-aromatic.
Non-aromatic. If I choose to be planar, okay, we have that requirement. It's fully conjugated, right?
Aromatic, yeah.
How many pi electrons in total?
No, but it'd be.
Oh.
It's 8 pi electrons, which means it's anti. What am I gonna choose to be? Non-planar or planar? Non-planar, exactly. Now, do we see it now?
Yes.
We're good with the chapter now.
Yeah.
Okay.
I don't know about good.
Oh, wait, okay, we don't know what to do. Okay, it's clicking. That's good. It's clicking. Yeah.
Okay, okay.
Let's say that I put a little oxygen in there that's double bonded. We would still have 8 pi electrons. So in that case, it would only be anti-aromatic.
No, no, add the oxygen and remove the double bond.
You know what I mean? So, and this.
Then it's not fully conjugated.
Okay.
So non-aromatic. Whoops, wrong one.
Right.
Yes.
Makes it 23.
Okay.
And it follows anti-aromatic.
It's the same process that we saw with the heteroatom. It's one of the rules that we're adding basically. So we know the requirements for the 3 different systems. Then we talked about the rules of heteroatoms. We know that single bonded heteroatoms, they can choose to be sp2 or sp3. Here's the thing, whenever you have rings that have 8 or more members, they can have a choice as well. 8 or more. Okay, this little guy, what is it?
It's cyclic, okay.
It's cyclic,
Yeah.
it's planar,
Fully conjugated.
it's fully conjugated,
It could be either because it's over that. Over how many splits? 7?
8 or more.
8 or more, okay.
I think. 14 pi electrons.
Yeah.
Oh, that's aromatic, it's aromatic, it's aromatic.
There you go, so
Yeah.
it chooses to be planar.
How does something choose to be bigger? That's what I'm not getting.
Yeah, I'm not sure how to answer that question. I've had that question before, but no idea how to actually, oh,
So aromatic and anti-aromatic?
yes.
Non-aromatic. Because
That's not one of the ones that are written in there. It's a new one that we're adding. 8 or more carbons in a ring. That means that they can choose to be planar or non-planar.
because if it were to be planar.
That's what happens. If they're non-planar, then you're breaking one of the rules, so it's gonna be not aromatic. If they choose to be planar, depending on the pi electrons, it's either gonna be anti or aromatic. In that case, it was anti, so we're gonna choose to be non-planar, so it's more stable.
Then we go to aromatic.
That's like the way of being. Oh.
Question. Air means carbons, oxygens, nitrogens, any atoms that are inside the ring. Hydrogens do not count.
Does it?
So, yeah.
So I felt like he was gonna be like, oh, I already made it.
Starting to adjust the
Okay, and guys, if you wanna try the problems on your own, the rules are listed here, okay? So you can take a picture right now. It's the heteroatom rules. Then it's the choice of the 8 or more member ring. It's on the right, and then on the left side, I gave you what carbocations, carbon ions, and radicals contribute to. And then the carbonyl group, we're gonna talk about that one right now.
Oh, this isn't posted on campus, is it?
No, I just did it. So take a picture of that if you wanna do the next few problems. Yes, but in this case, I added the planar, non-planar thingy for the carbocations, carbanions, radicals, those guys.
Are those like actually, or like, those are actually down there? Like, are those?
It's down to say.
And sometimes
Yeah.
they're big.
I'm trying to go on these full time, but I can't.
The whole.
Okay. Are you ready to do some more practice problems?
Oh, there's attempted.
Okay, actually, no. Let's jump right into this one. This molecule, is it cyclic?
Yes,
Is it planar?
Yes.
Is it fully conjugated?
yes.
Yes, exactly. Remember, automatically, those ones sp2 always. Now, here's the thing. How many pi electrons do we have?
It's the double bonded hetero that donates two. One.
Here's the thing. That heteroatom is not inside the ring. It's sticking out of the ring. So we're not using that rule. Technically, whenever you have any carbonyl groups, anything that's sticking out, it's not gonna donate anything. So we can cross it out and we can just draw a little carbocation there, because at the end, they both mean the same thing. You don't donate any pi electrons.
So in that case, yeah. Or
We have 4 pi electrons, which means that it's
anti.
beautiful.
Wait, why'd you just cross out the O? The little bond?
It didn't matter.
It doesn't contribute anything.
Oh,
Anything that's sticking out of the molecule is basically acting like a carbocation.
So this is specifically for rings, this is ring string. Okay, the question
So
regarding.
yeah, and it's right there.
Regarding the group that you had put up, you said that, on the right side. If a ring has 8 or more members, it can choose to be plain or non-plain.
Yeah.
But
Yes.
in the example of the, little triangle looking oxygen. Right there, first example. So it can choose to be non-planar or planar.
Whoa. How many members do you have in that cyclic structure?
It's got a lot of carbons.
You have 1 oxygen, 2 carbons, total of 3 members.
That's it.
So that rule is not applying in there.
Might have to be 8 or more.
Exactly. As long as you have 8 or more members, that's when it can choose to be planar or
Yeah,
not
But
planar.
that's what I'm saying, like, this molecule can choose to be non-planar, or it can choose to go in the sp2 form, can it not?
No, it cannot choose in this case. Again, it's
So we
based,
will never find it in the sp2 form, in nature. Or like it will be.
you're gonna find it, but it's not gonna be the most stable molecule that you see out there.
Okay.
Okay.
So navigability wants it.
Another question in regards to that last one, we crossed out the one that oxygen.
Mhm.
Did you say anything sticking out of a ring or just anything double bonded sticking out of it?
Let's just keep it to anything double bonded that's sticking out of the ring. Yeah. I haven't seen that example so far, but still, like, I don't want to make that generalization because I'm not exactly like 100% sure. So if you see that on lecture, then yeah, take a picture of it. I'll take a note of that. But otherwise, I haven't seen him do that before. Okay, we just have a minute left. So how are we feeling on 14?
Not too bad.
Not too bad, thank you.
Once you get it, you get it.
Yeah, so chapter 14 is a lot about practicing the rules over and over again. Okay, so just keep practicing. Remember the rules, please. The next session, we're gonna continue with the rest of the molecules. We're gonna do actually some group work. So if you guys can work in advance, that would be great. So we can go faster and we can finish the entire chapter 14 handout. Okay? So that's it for the session. And actually, before we end up, little quiz. What are the 4 requirements for being aromatic?
Planar.
And Huckel's rule. What are the possible numbers for Huckel?
Oh, yeah, 2 big, yeah, okay.
As long as we get the first 2, that's good. Yes. There you go. Now, what are the requirements for anti-aromatic rules?
Oh, it's just the Hubble's rule, that's the thing.
Exactly. The only difference is the Huggles rule.
Yeah.
And that's the only highlighted portion in that chart that I gave you in the
But
first
it's
page.
less stable than,
Non-aromatic.
Yeah.
How do we know that something is gonna be non-aromatic?
when it breaks any one of the four.
Exactly. What's the rule for double bonded heteroatoms? How many pi electrons do they donate?
Two. Double bonded. one.
Double bonded, one. What about single bonded? Two. What if I have multiple single bonded?
Two each.
Two each, and do they have to agree on the hybridization or not?
No. They have to agree on hybridization.
They have to agree, exactly, very
Wait, so
good.
wait, was one SP3 and SP2, then.
That's not gonna be possible. They both have to be SP3 or both have to be SP2. Like we saw in the example in here. Those both
Oh,
oxygens,
I see.
exactly.
You wouldn't have like, what if it's two different heteroatoms? Is that thing?
So as long as they're single bonded heteroatoms, they have to agree. Even if it's oxygen, nitrogen, or oxygen, sulfur, things like that.
Okay.
Okay. Any last minute questions? Okay, we're good.
Boron is just like, it doesn't do anything. Right?
Yeah, it's like a carbocation. Mhm.
What if it's SP, boron SP? Boron always
According to the geometry thingy, I think so, yeah. But for this class, they're also gonna be SP2, but as far as contributing to the pi system, it gives you 0.
But boron, doesn't mean it's octet.
Boron, I think that's one of the exceptions that it doesn't form an octet. Yeah, so yeah. Okay, I'll see you guys Monday. We're gonna continue with the chapter. Again, give it a try on your own. Just give it a try.
Sorry.
Oh,